Okay. Hello, everyone. Welcome to lecture 9 of Deep Learning for Natural Language Processing. Today's topic about pushing boundaries of large language models, part 2. In the previous lecture, we talked about contemporary language models, talked about fine-tuning LLMs, extending LLMs, and we also covered reasoning and efficient training and inference. Today, we first talk about explainability, and then we will be covering mixture of experts. And lastly, we touched upon vision LLMs and diffusion language models just for the introduction. We won't delve deep into them. So first, let's talk about explainability. To give you some intuition about what we mean by explainability, imagine that someone is going to a bank and is requesting a loan. So this person gives his information, for example, how much money he makes a month and how much loan he's requesting. And the bank has a system that analyzes the user's information and then decides on whether it should or should not give the person loan. And it would be really good if we understand why the system is deciding the rejection or the exception of the loan request. And AI models that decide are getting harder to understand the reasoning behind them. And today we will be talking about that. So why do we even need explainable AI? First, it helps us improve our systems. For example, a system might decide the right decision, but for the wrong reason. And we need explainability to understand that and address that. For example, take a look at this picture here. So this is a medical image that is supposed to be an image of a person's lung, and the doctor should diagnose whether the person has pneumonia, which is a lung disease. So the AI system looks into the image and classifies it as disease, and the decision is correct. But when we look into the reasoning behind the AI system, we realize that the AI actually looked into the right top of the image, not into the lung area. So that's counterintuitive. It shouldn't be looking at the shoulder area. So scientists try to understand why this is happening. And the reason behind that was because at the top right corner of the image, the name of the hospital and the machine that was used to take this image was written. And apparently every person who was sent to that hospital and that machine had this disease. So it was really easy for the model to just look into that text and decide on the prediction. So that's a famous example, and we need explainability to address that. Secondly, explainability helps us discover new knowledge. Sometimes we recognize new patterns in the data, the patterns that we didn't previously know. And lastly, it's a tool for the end users. For example, in the banking system and the person who was requesting the loan, this person has a right to understand why his loan was rejected. What was the base that this model made the decision? Was it because of his low income? Was it because of other reason? Was it fair or not? So we will delve deeper into explainable AI, and first we will talk about its concept.
Sorry.
Yes.
I had a question about the term explainability, and is it synonymous with the concept of interpretability?
Not necessarily. They are used they are used maybe as the same meaning in some concepts, but I think interpretability could have other dimensions. Like, I should also look into it, but in the Discord, we can have a discussion about it. That was a good question. The question was, are explainability and interpretability the same? So let's talk about the scope of explanation. So an explanation could be just for a given input, or it could also be for a subset of input. For example, imagine your AI system is incorrectly classifying this cow image. This is a cow on the beach, and somehow the model is not able to classify it correctly. But this is one example. So the explanation behind it is just a local explanation. But sometimes the model makes a same mistake repeatedly. For example, a model can be fooled by every cow that is on the beach, and it classifies incorrectly. And so this we call global explanation. We can also look into it from another angle and divide them into anti-hoc and post-hoc explanation. So anti-hoc explanation is basically explanations from a model that are explainable by design. So some models like decision tree is basically has the explanation in itself, because at each node of the decision tree, the model is analyzing a rule and it is making the decision on each node. It's very simple architecture. But we also have post-hoc explanation, which is when the model is not explainable by design, but after the model prediction, we analyze it and try to come up with an explanation, or ask the model for some explanation. That's post-hoc explanation. And today we will be talking about this. Let's talk about the techniques that we use. So the popular choices and techniques are saliency explanation and textual explanations. So what do we mean by saliency explanations? Basically, saliency explanation is when we look into what parts of the input mattered most for the model's prediction. For example, in our long image, we look into which part of the image has the most effect on the prediction. And it has two methods. It has gradient-based methods and perturbation-based methods, which we will talk about in a minute. But other than saliency explanations, we also have textual explanations, where we can ask the model to generate an explanation alongside its prediction. And we can also use chain of thought prompting when we provide a little bit of reasoning in the prompt, and the model follows the same structure in its answer and gives us some reasoning. So let's go deeper into saliency explanation. As I said, it looks into the input and what parts of it matter the most. Imagine you are analyzing some text with a model for doing sentiment analysis, and consider that the input text is great service, thanks Don, and the model needs to decide whether this is a positive sentence or a negative one. And the model looked into it and decides that this is a positive sentiment, but then we look into what parts of the sentence and which tokens mattered most. The model looked into the highlighted token, and the word great, service, comma, thanks, and the dot at the end had impacts, but most impacts came from the dots and the comma. And that's also a bit counterintuitive. We didn't expect that to happen, but somehow model found it very important. Also, our CAT scan image for the lung, we talked about it quite a lot. So let's talk about the methods we have in saliency explanations. So first we have gradient-based methods, and we also have perturbation-based method. So gradient-based is when we try to understand by making a small change in the inputs, how will the output change? We're not trying to completely replace or completely remove some part of the input. We're just trying to understand if I change this pixel by this amount, what will happen to the output? And for doing this, we need to have access to the model weights and parameters, and the gradients are important to us. So that's a requirement to do the gradient-based method, but we also have perturbation-based methods where we don't need the model weights to be only need to have access to the model input and outputs. So what we do here is we replace some part of the inputs, or we remove some part of it completely, and then we see what happens to the prediction. And by doing that, we can totally understand which parts are having the most impact. So as I said, next to saliency explanation, we have we also have textual generation explanation. Let me put this on the right. So okay. So this is when we train the model to produce the explanation alongside its prediction. And for that, we need to have the training data for it. So we need to have some ground truth explanation to train the model on. And to give you an example, look into this example. Imagine the model takes as input two sentences, one premise and one hypothesis, and it's deciding on the relationship between them, whether it's entailment, neutral, or contradiction. So we can train the model to predict this label as well as producing a text explaining it. And here the model predicted the label and also gave us some explanation for the reason behind it. Note that this explanation is also all-regressive, and there still exists the risk of hallucination here. We also have chain of thought prompting. As I said, this is when we give a bit of a structure and reasoning in the input. We talked quite a lot about it in the previous lecture, so I'm not going to get deep into it, but when you give the model some instruction and some reasoning, the output also follows the structure, and it basically explains why it is deciding on the output that it is giving. Yes, please.
Yes, I would like to ask a question about the structure of generating answer and explanation. Is it possible that a language model can develop a sort of confirmation bias? So, for example, it generates an output, and then since it cannot change the output, it kind of tries to confirm it. You can just structure the explanation in a way that suits the answer.
Yes, so the question for the recording is that am I understanding it correctly? So when the model produces a label, the explanation is biased towards justifying that answer, right?
Yes.
So yes, you're totally right. This could be the case, but I think when you explain it on really good data and where the label is correct and the explanations are correct, the model actually learns something, learns to provide you with good explanation. And of course, the risk of this still exists, but it doesn't really rule out this method at all. It still is a valuable and legit method to do. So let's talk about the evaluation of our explanation. So what do we call a good explanation? The reality is explanation could be viewed differently from different users. For example, a lay user, which is like a doctor who uses this AI system, uses an AI system for analyzing the CAT scan. So that's a lay user. And we also have developer and researcher. They have different interpretation of what is a good explanation. That's one thing to keep in mind, but the reality is explanations could be looked into from two angles. So they need to be plausible and faithful. So the plausibility is when the explanation makes sense. And it is important for a good explanation to be logical. But we also have faithfulness, and this is basically saying that does the explanation actually reflect the system's reasoning process? So the model might produce you a good explanation, something that looks good and looks logical, but it's not really the reason behind the model's decision. That's also important.
Sorry.
Yes.
The previous slide, what does orthogonal dimensions mean in this context? How does this apply to plausibility and faithfulness?
Basically, it means that these two are not necessarily the same. Like they might be viewed as being the same thing, but there are two different dimensions.
Okay.
So in machine learning, when we try to compare models and understand which model does better in a job, we usually use leaderboards, and they are the norm in the community. But what could go wrong with them? Is there some problem in it? Like, can it be problematic? And the answer is yes, a little bit. So Goodhart's law says when a measure becomes a target, it ceases to be a good measure. And what we mean by this is that when every researcher is focusing to beat a benchmark and be better than other counterparts at a specific task, sometimes that task loses its legitimacy in actually evaluating the model's performance in real life cases. So to explain it better, I provided this example. So there is a benchmark called ARC-AGI, which its purpose is to measure general intelligence. So it consists of some tasks that humans can achieve near 100% score in them. This is an example of a task from ARC-AGI. So you are given some pair of solved puzzles. For example, here you are given two pairs, and there is an underlying rule between these pairs. And here the rule is that a square should be filled with a yellow square, and it should make a full 2x2 square. And that's something that human can easily understand and apply it to a new one when they see one. And the tasks of ARC-AGI look similar to this. So what happened here was that labs and researchers tried to get really good at beating each other and getting top score in this benchmark, and they achieved near 80% accuracy in ARC-AGI 1, which was the first version, which was pretty good for an AI system. But then the people who were in charge of this benchmark changed the task a little bit. And what happened was that most model and pretty much every model that did really good in ArcAGI1 did pretty bad in ArcAGI2. So in other words, the model's performance plummeted, and the reason was because everyone was trying to just get really good score in the benchmark. So we can't say for sure that the model are actually getting good at general intelligence by just looking at the benchmark, as we saw what happened with when our AGI2 got released. So the story after was that model tried to get better at ArcAGI2, and they were able to achieve good scores in ArcAGI2 as well, but then ArcAGI3 got released, and what do you think happened? All the previous top scores again failed. So lastly, we will talk about how humans look into the explanations generated by the AI, or how we perceive those explanations. So one thing to first look into is a phenomenon called cognitive bias. So here in this image, you are seeing some dots, and do you guys see any pattern here when you look into the image? Yes.
I see some kind of animal.
Animal.
Yeah.
Yeah, that's one way to look into it. Good. And someone might see some clusters, someone might see some different shapes here, but that's how we humans perceive informations and data. But the reality is, these are just random points. There is no structure here. You like to impose a structure, but the reality is there is none. And that's what we call cognitive bias. And how does this, let's look at how does this affect the perception of the explanations. So let's look into our example of sentiment analysis on great service taxon. We said that the model looks into the tokens, and it decided that the word service, thanks, and comma, and the point at the end had the most impact. And the comma and the dots were really important to the model. Someone, a human, can look into this explanation and see that, okay, the word great was also impactful, and the word thanks, so the model is doing really good. It is looking into the word that it should look into and giving me the answer. So that's how a human mind likes to look into the phenomenon. But the reality is the model didn't really care too much about the word great. It cared a lot about the comma and the points at the end. So that's a wrap up for explanation. And now, who's ready for a quiz? Okay. We covered explainability. Now I want to talk about mixture of experts. So mixture of expert is a technique that uses different experts to improve the quality of LLMs. So each expert is basically a subset of parameter that we somehow involve in our architecture. It's just a feed-forward neural network, and when we have multiple experts, at least one should be activated. It could be more than one as well. And there is a router that decides which expert or experts should be activated. And so each layer has multiple experts, and each expert is specialized in something specific. And by a specialization, we don't mean that one expert would be good at handling psychology, another would be good at handling math. No, not like that. This specialization would be in a way that one expert could handle punctuation better, and another would be better with verbs and so on. So we have a router on top that should decide on the selection of the expert. So the model kind of looks something like this. We have a router and some layers, and each layer, one expert, or more than one. Here in this picture, one was chosen. And keep in mind that the model is still a single and unified, unique model. These experts are just subsets of parameters. So let's now look into where we would put these experts into the transformer architecture. So the vanilla transformer architecture looks like this. You have your input tokens, then you add positional embedding into it, and then you feed it into the decoder blocks. And each decoder block consists of a layer norm, a masked self-attention, and then another layer norm, and a feed-forward neural network at the end. And this feed-forward neural network is very important. It actually uses the contextual information created by the self-attention mechanism and uses it to capture more complex relationship in the data. Now, what does this feed-forward neural network looks like? In a vanilla transformer architecture, it's just a dense model. So you have some layers at the top, then it gets usually bigger. For example, here you have 512 neurons, then 2048, and then it downscales to 512, and you get your output. This is a dense feed-forward neural network. Now, a sparse model, on the other hand, divides those parameters into experts. So each expert would be a subset of those parameters that you just saw in the previous slide. And we wouldn't activate all of the parameters for each pass. We only activate one or two experts, which would be subset of total parameters in the model. And looking into the transformer architecture once again, if we use experts, it looks something like this. And you should also keep in mind that for each generation path, an expert will be chosen. So at each layer, one expert is chosen here. But the thing is, these will change for each generation path. For example, here, this set of experts were chosen, and for the next token, the selection of the expert varied. You have different paths. And what is deciding on that path and selection of the expert? That's, of course, the router. So the router and the routing mechanism at its simplest, purest form looks like this. So you have your input X, and the router could be just a matrix of weights. So your input gets multiplied by this matrix, and you get an output matrix. And what will you do next is that you put it into a softmax, and you calculate the probability for each expert. So you get a probability. For example, here we have 4 experts. We have a specific probability for each expert. And in this design, the expert with the highest probability got chosen. And what we will do here to calculate the output is that we multiply the output of this expert with the probability that the softmax assigned to it. And if we want to have more than one expert, what we do is we pick the top 2 probability of the softmax, and we multiply those probability as a weight into the experts' outputs, and then we sum them up. So as I said and repeated a few times, you don't have to pick only one expert. You can pick more than one. And in fact, picking more than one is the better choice. And a common choice that seems to work quite well is taking the top 2 experts. And why that's the case? Why am I saying that taking more than one expert works better? So the reason is that it helps with the stability. So if you only pick one expert, there is the risk of overfitting to only one expert at each layer, and the other ones may just not learn anything, and they get picked very few times in the training. So for the stability reason, you usually pick 2. Now let's talk about a famous model that used this MOE architecture to improve its performance. So Mixtral 8 times 7 billion is a sparse mixture of expert model. It activates 13 billion parameters per token, and its result is competitive and sometimes even better compared to Llama 2, which has 70 billion parameters, and GPT 3.5, which has more than 100 billion parameters in it. So the naming of Mixtral 8 times 7b, it comes from, so it has 8 experts at each layer. So that's what the 8 stands for. And previously, the author of Mixtral had another paper called Mistral, and it had 7 billion parameter. So what they did is they said, okay, we're going to have 8 times of the experts, 8 times of the feed-forward neural network in the Mistral, and we make it another model called Mistral. But keep in mind that the total weight would not be 8 times 7, because some parameters are shared. For example, the self-attention parameters are shared and the embeddings. So the total would be lower than 56 billion, and the total is in fact 40, near to 47, I think. Now let's talk about the advantages that MOE brings for us. So the whole deal, not the whole deal, a really good advantage that it brings is the model doesn't have to activate all of these parameters. So basically it brings us compute efficiency. Imagine you have in the Mistral example, you have a model that has close to 47 billion parameters, but only activates 13 billion of them at each generation path. So when you have the compute efficiency, you can have bigger models with the same computational power. And having the ability to increase the model size helps you store more knowledge into your model. And lastly, it helps with faster convergence. So research from Google has shown that the models that utilize mixture of expert reach the same level of validation loss compared to their dense counterpart in really much a smaller time. And sometimes the speed up is up to 7 times pre-training epochs or steps. So we also covered mixture of experts. Is there something unclear? If you want that now, that's the time to ask. Otherwise, we can move on to the next topic, which is vision LLMs. So this is a really huge area to explore, but today we will just talk about it as an introduction level, and it will not be included in your exams. It's just for your interest, and if you want to go down into vision LLM as your research path. So we saw that language models are capable of doing many things. For example, they can do coding, they can do math really well, they can do sentiment analysis. So there is this idea, if they're really good at doing plenty of tasks and basically it's a great architecture, can they handle images as well? Can we feed images into them and get something meaningful out of them? And the answer is yes, actually, we can treat the pictures as input tokens, but you have to process it some way. For example, one of the premier works is the Vision Transformer architecture, and the idea was to feed an image into the transform. So what should we do? How should we treat and convert an image into tokens? So what they did was they divided the input image into different patches. And after that, they linearly projected those patches into a flat array. So that flat array could be treated as an input token and could be fed into the transformer. You also have to add the positional embedding into it. And for this architecture, it also has a special token in the beginning before all these image patches. And I'll tell you in a few seconds what's that for. So we will feed these tokens into the transformer and we will get the output. But what output matters the most to us is the output of that special token in the beginning. So we use this output for downstream tasks, for example, classification and so on. So this was a really successful architecture, but what it did was it only analyzed an input image. It wasn't able to take image and text together as an input. Another foundation model was called Lava. It took image and text together as its input. So how was that possible? So it had an image, and for turning it into something meaningful to the LLM, it used something called the vision encoder of the clip architecture. And I will talk about that in the next slide, but for that, just think that it will take the image and turns it into an embedding that is meaningful, that is actually representing the image as some matrix. So it has the clip encoder, and then it has a linear layer. So this linear layer should make this clip embedding into something meaningful that the LLM can understand. So you get your tokens out of it. You also have your input text, and you feed them into your transformer architecture. And you can, for example, do image captioning. You can do plenty of tasks with this. But the whole deal was that it was able to take text alongside images as input. And this is called the unified architecture. We have some models that have different transformer for analyzing text and analyzing images. Then they do cross attention to get some output that's considered them both. But here it only used one. It was unified, in other words. And in the Lava architecture, I stated that it uses clip encoder. So what clip encoder is, what clip basically is, it is a model that has two encoders, a textual encoder and an image encoder. So for training it, you need to have pairs of image and captions. And you divide your training into batches. And for example, consider batch of 8. So for training it, you put a batch of 8 text into your textual encoders and a batch of corresponding 8 images into your image encoder. And what you want ideally is to have a high cosine similarity between the corresponding parts and a low cosine similarity between the text and images that are not in a pair. So what this does, it uses a contrastive loss that basically does what I just said. And at the end, what you get is a text encoder that is really good to get some meaningful embedding out of the text, and an image encoder that is good for getting embedding out of an image. And usually they are widely used in downstream tasks. Okay, last but not least, we will talk about diffusion LLMs. This topic is also not exam relevant, but it is worth mentioning. So some of you might already be familiar with diffusion models. What diffusion models are, they take an image as inputs, they add noise into it in the forward pass, and they get to pure noise. And this noise is just a Gaussian noise. And there is a backward and reverse process where the model tries to denoise this pure noise and gets back to the initial image that was given in the beginning. So this is, in very simple terms, how a diffusion model works. It has multiple steps, usually 1,000 steps at the vanilla DDPM, and it trains a neural network to learn to be able to denoise. But the key intuition that was taken from it and were translated into the text was adding noise into an image. So we have to figure out a way on how can we add noise into text or do something similar. And also iterative refinements. We have to be able to achieve to a meaningful output by just analyzing something that is pure noise. So a very famous and fundamental paper and model that's used this technique and basically utilize it on text was called LADA. So let's see how LADA dealt with the problem. So as I said, one problem was to figure out a way to add noise to the text. And of course, it's not an image, you can't add Gaussian noise to it. So what they did instead was they masked some tokens in the input. So for example, if you want to add 10% noise to your text input, what you will do is you will mask 10% of your input token. And by that, basically you solve the first part of the problem. Now you want to train your model to be able to unmask those masked tokens. It has two stages of training. First, you give it just a sequence of tokens and some parts of it are masked. The model tries to unmask it. Very straightforward. Then you divide your inputs into prompt and response. So here, the prompts will not be masked at all. Only the response will be masked partially. And the model will learn to unmask only the response. And at the end, when you want to run inference and use the model, you give it the full prompt and you give it a full mask token sequence as a response. And what this model does is that it starts generating the response as groups of tokens at each step. So a key difference here from other regressive LLMs is that it doesn't generate outputs only one token at a time. It generates them group by groups. Now let's talk about the advantages, the key features, and the limitations of Diffusion LLM. So a cool advantage that they have is that they can generate tokens in groups. So the generation does not need to happen at the sequence length. The iteration is less. And another cool feature about them is that they can model dependencies in both directions, not just from left to right. They can also look into the future tokens. And here, they might have some advantage in reversal reasoning compared to the other regressive counterparts. And I'll also have a demonstration of how diffusion LLMs work. I'll show it to you in a few seconds. You can see that sometimes the future tokens are generated and then the previous ones are generated. And also there's limitations. There's reasons that they are not the mainstream for NLP tasks these days. And a huge limitation is that the generation length is a user-specified hyperparameter. So that's a little annoying. And moreover, the quality of the output is highly dependent on the amount of tokens that are generated at each step. So if you generate a lot of tokens at each step, of course, the quality is really bad. And if you try to generate only a few or even one, then that is kind of against the throughput advantage that it gave you in the beginning. And let me also show you how basically diffusion LLM works. So you can have a look, and as you can see, they are appearing as multiple groups at a time, and it doesn't start from the beginning. For example, the last token is also generated in the beginning of the iterations, and then towards iterations, it gets filled. Okay, thank you guys for listening. Before wrapping it up, I would also like to mention that at the 30th of June, we have a guest lecture here. Feel free to tune in if you like. And at the 7th of July, we have your exam simulation. If you like, you can also attend that. Thanks for listening.
So was it? Okay, yeah. So everything. It's okay, actually. It's okay. So you got everything recorded?
Yes, I will send the.
Okay, cool. So I'm taking this back and this back as well.